Okay, so now looking at this learning check, we had two groups of acids, and we are listing them weakest to strongest. So the difference in this first list, A, B, C, D, is the number of oxygens. Oxygens are electronegative atoms, so having more oxygens present in the molecule would result in a stronger acid. So this is because of the inductive effect. Both of these lists the inductive effect will be relevant. And so over here, weakest acid will be the one with fewer oxygens. So HIO will be weaker than HiO2, weaker than HiO3. And HiO4 is the strongest with greater number of oxygen atoms, electronegative atoms, increasing the acidity. Then the other list of acids are all analogs to acetic acid, which is shown at the top there. The Lewis structure of it is shown. In the first one, instead of having a CH3 group on the left side of the molecule, it has a CF3 group. So we have trifluoroacetic acid. Those hydrogens are now fluorines. Second one, there is one of those hydrogens replaced with a bromine. Third one is just acetic acid. And then the last one, all three hydrogens are replaced with chlorine. So in all of these, except for C, so A, B, and D, a hydrogen, not the acidic hydrogen, one of the hydrogens bonded to carbon is replaced with an electronegative atom. So again, the inductive effect is relevant here. Having an electronegative atom elsewhere in the molecule increases acidity due to the inductive effect. So the weakest will be acetic acid. I'm just going to write the letters, so C for option C. And then the strongest will have the greatest number of the highest electronegative atoms. So we're thinking about fluorine versus bromine versus chlorine. Bromine is the least electronegative. It's the lowest on the periodic table. So if you were to look at the periodic table, fluorine, chlorine, and bromine are all halogens, but bromine is in the lowest row. So that's the least electronegative. And in molecule B, we only have one bromine, where in A and D, we have 3 chlorines or 3 fluorines. So B will be second weakest. And then now we're comparing having 3 chlorines or 3 fluorines. Fluorine is more electronegative than chlorine, so that will have a stronger inductive effect. And so A is the strongest. Yeah. Yeah, so it's the same effect having more electronegative atoms present and more, like a greater number of them and higher electronegativity of those atoms will increase acidity. In this one, the atoms aren't changing, the identity of the atom isn't changing. We still have hydrogen, iodine, and oxygen. But over here we have 4 oxygens, and oxygens are also electronegative. So having a greater number of them, again, pulls electron density away from the acidic hydrogen, which makes it more acidic. Because then the hydrogen has a greater partial positive. So let me go back. So just like on this slide, we identified this out of all the hydrogens as the acidic one because it has a greater partial positive charge. Electron density is pulled away from it by the oxygen. If you add other electronegative atoms over here, that has a similar effect of this oxygen where it's pulling electron density away. So a greater number of high electronegative atoms will make this more positive. So that's what we see in that first trend. We have greater number of oxygens, which makes that one more sense. Other questions here? Okay, then we will move on to the last section of chapter 16. So last type of Lewis acids. I'm sure you got a preview of this if you worked on the Achieve homework. So this is a more broad and just different definition of an acid and a base. And so these acid-base reactions, Lewis acid-base reactions, don't involve a proton transfer. So the acid's not giving away a proton and the base isn't accepting a proton. It's more focused on the electrons that are being shared between the acid and the base. So the Bronsted base is called the proton acceptor. That's what we've labeled it as. And the base can accept a proton, can accept that H+, because it has available electrons to create a bond to the H+. We said that the Bronsted definition of the acid is a proton donor. For Lewis definition, bases are electron pair donors, and acids are electron pair acceptors. So just like we're focused on bases, just like Bronsted bases, which have a pair of electrons that they can give away to a hydrogen, in the Lewis definition, bases have a pair of electrons that they can give away. It's just not specifically to a hydrogen in all cases. Lewis bases provide electrons to create a bond with the acid. So in this example up here, the nitrogen is the base, H+ is the acid. That nitrogen pair of electrons on top of the nitrogen, if you look at the product, it doesn't have a pair of electrons anymore. Instead of owning that pair, the nitrogen is sharing electrons with that hydrogen atom, and that's how we get that NH4 molecule. So here's another example on the next slide. A Lewis acid often has an open valence shell. Meaning that it can accept more electrons into its valence shell. And then bases have an available pair of electrons. So Lewis bases have an available non-bonding electron pair, so 2 dots on the atom. That's how we represent it. And then the acid has an open valence shell. Lewis acids are electron acceptors, so they have to have an open shell to accept more electrons. Bases are electron donors. They will donate and share electrons with the acid. So in this example, we have one open shell atom. That atom will be the Lewis acid. Each of these fluorines have 8 electrons around them, so they're not open shell, but boron only has 6. So boron is one of those atoms that's stable with an open shell. It has 3 bonds, 2 electrons per bond, that's 6 electrons. 8 electrons would be a closed shell, but it only has 6. So open shell atom, and then in the other molecule, we have a pair of electrons here that can share with the boron. And in the product, now we have a shared electron pair between them. So the base, electron donor to the acid, which is an electron acceptor. So just wrote a few notes there. Boron is open shell. That makes this molecule the acid, the electron acceptor, and then nitrogen is the electron donor. All right, we will do the next slide as a learning track, so I will get that started. So you have 6 atoms, ions, or molecules. Classify them as a Lewis acid or base. Lewis acid can accept electrons, so something that is either open shell or could become negative. And then a base is something that has non-bonding electrons that it can share. And then if you finish this early before I close it, go to the next slide after. That's another learning check. Okay, so acids have an open valence shell, and then bases have available non-bonding electrons. So those are Fe3+.
Wait, you know the 3 plus here?
Yeah.
So you have 3 plus and base, right?
But it does it have available electrons? 3 plus means it has lost 3 electrons.
No. So he has to.
Yes, but there are bases on the list where I didn't draw the list. You should be able to see that. So like if you were to draw the Lewis structure of that, would it have any non-bonding? Or is it open shell? Yeah, lost it. It is lost 3, so it gave away 3 electrons. It doesn't have
Wait, so acid
it has already lost electrons, but it could gain more. Yeah, it has electrons. No, so I announced it a few times in class. It's all of this semester and that semester. It covers Gen 1. We're gonna do review from Gen 1, but it's cumulative. Yeah, because so we're doing the BCS final, so it's created by the Emergency Chemical Society, and their final and their goal is to make sure that everyone is prepared to take organic chemistry the next term. And so they're just ensuring the goal is to like have you all students study Gen Chem 1 and 2, but a lot of what we learned in Gen Chem 1 is relevant to what we learned in Gen Chem 2. So most of it we just
mostly this one is like some questions about last week.
by unit you mean semester.
Yeah. So really, most of the questions are right. And like
So you're
Some portion of
losing
it,
C4.
Probably more of it is this semester.
yeah, like,
I don't know for sure. I've been looking. I mean, we'll do some review and it'll hopefully come back. Yeah. Say about 1 more minute.
I think we're right now.
Okay, say 10 more seconds. Get your answers in. All right, I will close it here. All right, I do want to see what we're all thinking for these. Okay, question 1, pretty good. So question 1, we have iron with a 3+ charge. That means it has lost 3 electrons. It's certainly, if it has already lost 3 from neutral iron, it's not going to give away any more, most likely. It also, as a metal, probably won't create a covalent bond, which is what a Lewis base will do. So if anything, it will accept electrons, so we will call this one an acid. So metal cations can be electron pair acceptors, and that's what we have there, Fe3+. See, CH4, a little bit more of a mix here. CH4, this is methane. I'm going to draw the Lewis structure just off to the side. And this would be helpful for covalent molecules to determine if it's a Lewis acid or base, or neither. CH4 in this case, there are no open shell atoms and there are no non-bonding electrons. So no open shell, it can't be a Lewis acid. No non-bonding electrons, it can't be a Lewis base. So this is neither. Okay, so all atoms closed shell, can't be an acid, no non-bonding electrons, can't be a base. Next we have Cl-. Cl-, again, this is helpful drawing the Lewis structure. Cl-, so chlorine's in the 7th column, it's a nonmetal, so we can draw these non-bonding electrons. -1 charge means it has gained an extra electron to reach that -1 charge. It's a closed shell. It has 8 electrons in its valence shell, but it also has a bunch of non-bonding electrons. So this can be a Lewis base. It can donate electrons to create a covalent bond. Next we have NH3, much better on this one. So NH3 we saw on a previous slide. Nitrogen has a non-bonding electron pair and 3 single bonds to hydrogen. Again, you can draw the Lewis structure to see this. No open shell atoms, but it does have an electron pair, so this can also be a base, as what we saw in the previous slide. Nitrogen was the electron donor, so it's a base. H2, oh, big mix here. Okay, so H2, drawing the Lewis structure, we have a covalent bond between 2 hydrogen atoms. Both hydrogens are closed shell. Hydrogens only need 2 electrons to be closed shell. So both of them are closed shell, and there are no non-bonding electrons. So this is neither. And then last, let's see what we said for this one. Okay, so I think A was acid, so for metals often don't have an anion charge, an anionic charge, so a negative charge. If anything, they'll give away electrons to become positive. So Fe is neither. So neutral metal atoms don't donate, so be a base, or accept, being an acid. So neutral metal atoms don't donate or accept electron pairs to form covalent bonds. So if they were to accept electron pairs, they would become negative, but that is unlikely for metals. They often become positive and lose electrons. And they also don't share electrons to create a covalent bond because they're metals, so they create ionic bonds. All right, we'll do the next slide together. Are there questions on this one? Okay, so next slide, we have 3 Lewis acid base reactions, and we're looking to find the Lewis acid and the Lewis base. First one, we have aluminum 3+. A cation is a good indication that you have an open shell atom. We also have H2O. We know for H2O, all atoms are closed shell, but oxygen has non-bonding electron pair. So aluminum with 3+ open shell will be the acid, and H2O will be the base. Yeah.
But if aluminum has a 3+ charge and you go back in periodicity, wouldn't that
Yeah, so just like, I don't know if we saw an example on it. We didn't see an example of this before. So aluminum, yes, it loses 3 electrons. If it's going to have a charge, it's probably going to be 3+. That gives it a full valence shell, but with the extra protons, it can accept more electrons. So it can accept 3 more to become neutral, but it would never accept more than that. So metal cations can be Lewis acids. Yeah. Okay, next we have O2-. So to have a -2 charge, oxygen had gained 2 electrons. Right now it has a full valence shell with 8 total electrons, so it cannot accept any more. So it must be the base, and the other must be the acid. Last one, we have water again. All atoms are closed shell in water. Oxygen has 2 non-bonding electrons, so that must be the base. H+, open shell, that'd be acid. So for Lewis acid-base reactions, you should be able to identify something that can accept more electrons. So that's either something with an open shell, or in the second example, the sulfur. I'm not sure if we've used this word before, but I'll write it anyway. It's a hypervalent atom. It's in the third period. In third period, elements can hold more than 8 electrons. So we know for sure oxygen, O2- can't accept anymore. It's in the second row. It can only have 8 electrons in its valence shell. It already has 8. So it can't accept anymore. Other molecule has a hypervalent. Or can hold third or higher period, well, really lower on the table, can hold more than 8 valence electrons. This is because the third period, fourth period, fifth period, they'll have access to the D shell. So in the D shell, you can have an extra 10 electrons. Okay, questions on this page? Okay, we'll go to chapter 17 for a little bit. We're going to learn about buffer solutions. I understand if you're in lab, you've done some work with buffer solutions. So we'll spend some time talking about those in class now. All good on this page? Anyone still writing? Okay. All right, chapter 17 is all about aqueous equilibria. So we're thinking about equilibrium reactions in aqueous solutions. We might have ions dissolving, things like that. This is well, it's kind of hard to see on the projector, but a picture of red blood cells. Red blood cells are donut shaped when there is a balance of ions between the solution outside of the red blood cell and inside the red blood cell. Changing the equilibrium between the inside and outside will either have the red blood cell shrivel up or expand. And you don't want either one, but sometimes that does occur in certain conditions. So we're going to talk about what buffer solutions are, the Henderson-Hasselbalch equation. We'll talk about titrations, indicators, and then the last 2 sections are about solid solutes. So KSP are for solids, and we'll talk about Q again and K. Okay, but we'll start with buffer solutions. So we'll explain how buffers work and then calculate pH changes in buffer solutions after adding strong acid or strong base. So think about your lab as you're learning or as we go through these slides. So in general, buffer solutions resist a change in pH by neutralizing any other acids or bases that are added to solution. So because of everything that's already present in a buffer solution, you can think about it as buffering the pH change. So it resists any change to pH. if you're adding other acid or bases to solution. And a buffer solution is made of weak acids and weak bases. So some examples, human blood pH is 7.4, and that is a buffered solution that is very unlikely to change because it has both weak acid and base present. Ocean water pH is about 8.1. Again, resistant to change. Baby lotion has a pH of 6. There are a bunch of other examples of buffered solutions, but those are some. And so an example of creating a buffer solution, well, we need to consider the common ion effect. So if you were to add HNO2 to water, now note that this is a weak acid. It's not on our list of strong acids. HNO3 is a strong acid. HNO2 is a weak acid. So if you add HNO2 to pure water, it will act as an acid. It will donate a proton and produce some NO2 minus and some H3O plus. But a lot of it does remain as HNO2 because it's a weak acid. That's our definition of weak acid. The K will be less than 1. So there isn't a lot of the conjugate base, which is here. NO2 minus present. But to create a buffer solution, you add both the acid, so HNO2, and the conjugate base, NO2 minus, in some form also has to be added to solution. So you're increasing the concentration on both sides of that reaction equation. So if sodium, NaNO2, was added to the same solution, what happens to that equilibrium? Well, NaNO2 would separate into Na plus, NO2 minus, we're increasing the amount of NO2 minus in solution. Remember Le Chatelier's principle. That means that reaction will shift to the left, equilibrium will shift to the left. So I was at the end of chapter 15. So equilibrium shifting to the left, we can say HNO2 ionization is suppressed. So there's both HNO2, the acid, the weak acid, and NO2 minus, the conjugate base, both are present in solution. So if both HNO2 and NO2 minus are added to solution, that would be an example of a buffered solution. So buffer solutions have significant quantities of both a weak acid and its conjugate base. Or we can say vice versa, a weak base and its conjugate acid. So both must be added by the person preparing the buffer solution. Just adding the acid doesn't produce enough of both the acid and the base. So an example would be if both HNO2 and NO2 minus are added to solution. So remember, buffer solutions resist a change in pH. So if you prepare a buffer solution by adding HNO2 and NO2 minus, and then another acid or another different base is added, the pH of that solution is resistant to change. So it won't change as a result of adding that additional acid to a certain extent. But this allows equilibrium to shift in either direction according to Le Chatelier's principle when acid or base is added. Let's say other. All right, we're not talking about the acid or base in the buffer solution, but other acid or base added. Okay, so next slide, we have an image of a buffered solution, HA and A minus. If you add more acid, the equilibrium will shift left where we have more acid present and less base. And then if you add more base, the equilibrium will shift right. But either way, we have both conjugate acid and base present, or acid and conjugate base. So next slide, we're looking at what combinations can form a buffer solution. So let's see. We'll start that here. So HCl and NaOH, adding those two solution, can that create a buffer solution? And then the next two examples as well. I think all three are an iClicker question. Say about 30 seconds. Looks like we're almost done.
Wait, no.
right, all set? Good, submitted? All right, I'll close it. All right, first reaction, we have HCl and NaOH. What do we know about HCl? It's a strong acid, yes. NaOH? Strong base. So HCl and NaOH, if you add them together in solution, we'll have sodium cation, chloride anion, and H2O. We have to have a weak acid or a weak base, or a weak acid and its conjugate base, or a weak base and its conjugate acid present in solution. In this case, there would be no conjugate acid, conjugate base, right? We have those spectator ions that don't influence acidity or basicity. So this one is not a buffer solution. We'll say no, because it is a strong acid and strong base. We need a weak acid or base to have an equilibrium reaction. This would not be an equilibrium reaction. HCO3 and CO3 2 minus, these differ by one hydrogen, one H plus, and neither is a strong acid or a strong base, so this would work. This is a conjugate acid base pair. We have a weak acid and a weak base, so that can create a buffer solution. HBr and NABr. Hydrogen bromide, this is a strong acid. They are conjugate pairs. They differ by one H plus, but HBr is a strong acid, so that can't create a buffer solution. It'll fully ionize, and in solution, you'd have 0 hydrogen bromide molecules. In the buffer solution, we need both acid and base. Questions on this slide? Okay, 2 things. We are going to do a review of chapter 1. So I mentioned that the final has some content from Gen Chem 1 and 2. So we're going back to chapter 1. If you look back at chapter 1, hopefully it looks very familiar. It is unit conversions, a little bit of significant figures, like measurements, like a millimeter versus a meter, so real far back. So I have 2 iClickers to do, and then another thing that I want you all to be aware of is that, I don't think I mentioned this, so we are hiring another chemistry professor and another physics professor in the department. No one's leaving, we're just adding more professors to our department. Our first chemistry professor candidate is coming tomorrow. So if you're on campus tomorrow, I highly, highly encourage you, come back to this room at 12:30. Our candidate is giving a teaching demonstration and a research talk. So they're going to pretend to teach and then also talk about what research they would plan to do when they come. And then we want this room to have a lot of students in it because we really do value feedback from students when we make our decision of who to hire. So you'll have a form that you can fill out if you're here. And then also this is a really fun time for you all because you have a say in who gets hired and who will be teaching future chemistry courses, potentially courses that you're enrolled in. So I'll post an announcement to remind you all this Tuesday. So tomorrow, Thursday, and next Tuesday, we plan to have the chemistry professors, and then I'll let you all know when the physics professors are coming. But if you are on campus, please do come. I will start this review. So significant figure review. One is an old exam problem. So you had a graduated cylinder. I don't have the slide. Well, yeah, I'll get the slides up. One sec. But you'll have them on your phone right now. So one is a graduated cylinder, and you are just reporting the correct number of sig figs. And then the other one is the ruler. Oops. And then since it's 11:50, how about we review these two questions at the beginning of class? But you can take a few minutes to finish them. I'll leave it open. Well, that's all for today. Oh, if you didn't pick up your most recent exam, I have them here. Sonia?
Yeah, the 2 days that I've missed are the 2 days we've
Oh, really? That's funny.
Because I was gonna say, Edith, like my local mom just announced that it's like next Wednesday. I was gonna send you an email about it. It's gonna be included in like the 3 absences that we have. Or
Okay.
is it excused as like
Yeah,
a separate
just send me an email and then
I was a
I'll
little
let
worried
you
'cause
know.
I think I've hit 2 absences.
Have you?
already,
Okay,
yeah.
okay, yeah. Should be okay. But yeah, just let me know. Yeah. Okay.
No, you shouldn't have to, right? No, you just do a normal citation, not the back citation. Just the. Why don't you do one that's like, no, that's meant to be one, before we even talk about back citation. No, yeah, because she wanted to do that.
Yeah, let me close this.
If you were to do a back
And
citation.
then I'll
She didn't
get
want
the
you to
recording.
do it. Today's actually, it's like, no, this time.
It's what? Quicker? Oh, good.
I just wanted to show you the math to make sure I do it right.
Okay.